Okay, so here are the two things we're combining. We're combining the 21% with the 33%, trying to get 25%. So how much, the 21% is 0.21, how much of that do we have? X, that's what we're looking for. Plus the 33%, 0.33, how much of that do we have? 240 milliliters. That's going to equal 0.25, the 25%, times what? X plus 240. So now up here, 0.21 times X is just 0.21X. 0.33 times 240 is 792, or 79.2. Equals 0.25 times X. It's 0.25X. 0.25 times 240 is 60. Then what? We've got an X on each side. We've got to get rid of one of the X's. So it's 79.2 is all that's left over here. 0.25 minus 0.21 is 0.04X. Plus 60. And then subtract 60. Yes, we subtract 60. 19.2 equals 0.04X. And then divide by 0.04 is 480. So let's make sure we go back and see what that represents. That is the amount of the 21%. Our other amounts were in milliliters, so that has to be in milliliters as well. What do you think? Not horrible? Better than a sharp stick in the eye? Okay. More fun than a barrel of rabid monkeys? Gotta keep your options open. Yes. A reservoir holds 12 liters of coolant. It tests at 48%. You need it at, let's go 61%. How much should you drain and replace to get to 61%? Now what I'm talking about is we're going to drain part of this solution and add just pure whatever additive it is in the coolant, okay? So this is water with some sort of an additive in it. So we have the 48%. What percent is the stuff we're going to add to it? 100%. Good. Now we're going to expect to get to 61%. So for the 48%, that's 0.48. How much do we have? Let's do this. The 100% is 1.00. How much of that do we have? That's X. That's how much we're going to, however much we're going to drain, that's how much we're going to replace, right? 61% is 0.61. How much of that are we going to have when we're done? The reservoir holds 12 liters, period. It's going to be 12 liters in there. So now let's work backwards. How much does this have to be? 12 liters minus however much we took out. 12 minus X. Someone pause. Does that make sense, that 12 minus X? We had 12 liters in the reservoir and we had to take out a certain amount. So 12 minus whatever we took out. We still had to remove some of it from the reservoir. There's no room to put anything else in. So now 0.48 times 12 is what? 5.76. 0.48 times negative x is negative 0.48x. Plus 1 times x is x. And 0.61 times 12 is what? 7.32? Okay. So now we're going to combine these here. What is negative 0.48 plus 1? 0.52x, right? Positive 0.52x. And then, what do we have to do here? Subtract 5.76 is absolutely correct. 0.52x equals 1.56, is that right? And then divide by 0.52, x equals 3. So we would drain 3 liters out of the reservoir and replace it with pure coolant to get that percentage from 48 up to 61. Does that make sense? Okay. Let's say a solution is at 84% and you need it at, let's see, what do we want to do here? Let's go 60%. If it contains 1,200 milliliters, how much do you need to drain and replace with water? So now again, what are we starting with? 84%, and what are we mixing with it? What percent? 0%, and we're trying to get to 60%. So we have, okay, so 0.84 for 84%. How much of that do we have? 1,200 milliliters minus however much we're going to take out. Plus 0% is 0.00. How much of that are we going to add? X, right? Whatever we take out, we're going to replace it with water. That's going to equal 60 is 0.6 times 1,200 milliliters. So now we have 0.84 times 1,200. Yeah, 1,008. 0.84 times negative x is negative 0.84x. What's 0 times x? It's gone. It's done. And 0.6 times 1,200 is 720. So subtracting 1,008, we get 288 equals, actually a negative 288 equals a negative 0.84x. And then divided by negative 0.84. X equals a negative divided by negative is going to be a positive 288 divided by 0.84 is going to give us 342.85714. Technically that's 2857, but we'll round it off like the calculator does. 342.86, we'll say, milliliters. That's how much you need to drain out and replace with pure water to get it down to 60%. What do you think? Unless you guys get into dealing with hydraulic systems, like I said, heat treating and quenching, you'd be doing this. For you guys, if you needed to quench something, somebody else would be setting up the bath for you, the solution, for the most part. But there are steps above where you guys are training for that some of you may advance into at some point. Well, some people are content once they get there too. If you're happy with what you're doing, why worry about it? But if you get into like material, I can show you stuff with alloys and stuff like that, where you're mixing alloys and the temperature separation and things like that. If we get some time here towards the end of the year, I'll show you guys some of it. Remind me and I'll show you guys some of it. Okay, so now the next step we want to get into, we've already looked a little bit into stuff like this, where if I'm told that y equals 5m minus p over q, for m equals 8, p equals 16, and q equals 2. I can evaluate this. Evaluate is the command we would be given, what we'd be asked to do. 5m is going to become 5 times 8 minus p over q is going to become 16 over 2. Just replacing each letter with the numbers that it represents. And now we have to use our order of operations to reduce that down to a single number. 5 times 8 is 30 minus 16 divided by 2, 8, that equals 32. So I might be told that power is equal to voltage squared divided by resistance. So evaluate, find P when V is 12 and R is 16. So your power equals, what goes in here now? 12 squared over 16. Yeah, 12 squared is going to be 144. Divided by 16 is 9. So the power is actually what they call 9 watts would be the units, but I don't expect you guys to know the units there. If you're dealing with the area of a trapezoid, you might be told that area equals little b plus big B over 2 times h. So find A for B equals 12, big B equals 18, and h equals 10. So it's the same type of thing. Put in 12 plus 18, replace little b and big B with their numbers. Then it's order of operations. We have to work inside the parentheses, that's an enclosing symbol. But the fraction bar is also an enclosing symbol, telling us we have to do what's on top first. 12 plus 18 is 30. And now we have 30 over 2, which is 15. So we can get rid of the parentheses since we're down to a single number. Times 10 is 150. It might be that the force is equal to mass times acceleration. For example, let's say that you wanted to get your car up to a certain speed in a given amount of time. Well, there's an acceleration, required acceleration to get to that speed in that time. If you want to know how much force you have to apply to it, let's say the mass is equal to about 1,500 kilograms would be relatively average car. And let's say acceleration, you want a required acceleration of 10 meters per second. So the force required is going to be 1,500 times 10, which is going to give us 15,000. Now the units that would go into that would be newtons, but we're not going to talk about units of force for the metric system. What if we are exerting a certain amount of force? You have a known force. Let's say you are always exerting a force of 2,000 newtons. Force of 2,000, we're just going to say. And we're going to try different objects that we're going to exert that force on, that we're going to push on them with that force. And we want to figure out, theoretically, how fast they should accelerate. So what's going to happen is, we have force equals ma. We're going to change the mass to see how it affects the acceleration. Well, this would be a lot easier if we had this in the form of acceleration equals. Then we just had our force and mass over here, and we just plug in the numbers and multiply, divide, add, subtract, whatever, right? Well, that's one of the things we can do. Now that we know how to solve equations, we can solve them even without numbers in them, with just the letters in them. If I want to get a by itself, just like we did with numbers, we find the equal sign. Here's where the a is. What's keeping a from being by itself? The m. What operation is attaching the m to the a? It's multiplied. So to get rid of it, we divide. We divide and the m is gone. And just like when we had numbers there, we have to do the same thing to the other side of the equal sign, the other side of the equation. The difference is before we could actually divide out the numbers and get another number. Here, f divided by m is just f over m. So the acceleration that we're going to get is equal to the force divided by whatever mass we're using. Make sense? You could do the same thing. You could do mass equals and then force. It'd end up being force divided by acceleration, yes. Let's say your rate, your speed, is equal to a distance divided by time. And you want to know, you want to solve this for the distance. You want to know how far you can go in a given time at a certain rate. So the distance, what's keeping d from being alone right now? T. What's attaching it to the distance? Division. So to get rid of it, we're going to multiply. So that's gone. This was just d. R times t is just RT. What if I wanted to know at a given speed how long it's going to take to go a certain distance? I want to solve this for t. Well, one thing I could do is I just go back up and see this. Hey, I can solve it for d where r times t equals d and then divide by r, right? If you see that, that's great. You can just go back up and say, okay, I'm going to solve it for d first so that t is not on the bottom of the fraction anymore. And then I'll go from there. Because solving for something that's on the bottom of a fraction is tough to do. But one thing I can do is this. I can make it a proportion. Make that r over 1. How do I solve a proportion? Well, if I'm solving for this right here, if that were x or whatever, I would cross multiply 1 times d and then divide, right? So what's 1 times d? Say d. Yeah. Divided by r. So t is equal to d divided by r. I get the same thing here. RT equals d. If I divide it by r, t is equal to d divided by r. power is equal to current squared times resistance. Let's say I want to solve that for I. What am I going to do? Well, I has been squared and then multiplied by R, right? So to reverse that, I have to divide by R because that's the last thing that was done. So the R is gone over here, leaving with just I squared. Over here, P divided by R is just P over R. Then it's squared, so we have to square root it. So the square root of I squared is just I. That cancels out. The square root of P over R is the square root of P over R. Now I'm going to warn you, on the test, make sure the square root symbol goes down at least past the fraction bar. Every year I get people that do this. Yeah, that doesn't work. It's got to at least go down so that we know that the denominator's under that radical as well, that square root. What do you think? Well, you guys got plenty to practice, so make sure you still work on that 264. This is a repeat of the one from last hour. Exercise 6.6, that 1 through 25. Those mixture problems, they are very difficult, and that is one that when it comes to the test, a lot of people get wrong. A test which might come on Tuesday. By might, I mean it will. Also on page 267, exercise 6.7, 1 through 19, the odds. That's actually what we were just doing, taking formulas that are all letters and rearranging them so it's one letter, a certain letter equals the rest of them. And then finally, page 270, exercise 6.8, this will also be 1 through 25, the odd. This is those formulas where you plug in the numbers and do order of operations to get the desired value. Okay, I'll let you guys have our last 20 minutes here to get started on homework.